Hello, everyone, and welcome to this episode of our Inspiring Science Education Hangouts. This is part of a whole series of episodes that are put together to help you better understand big ideas in astronomy and physics that will help you better convey the excitement and discovery of modern science to your students. This is going to be the last video that we record during this particular 2014-2015 school year, but we will be back with the next school year, so stay tuned in September for a whole lineup of new topics, new science, and new scientists coming to you to talk to you about their work. Now today we're going to be talking about blackbody radiation. This is the radiation that pretty much anything that is not absolute zero gives off. So whether you know it or not, you're currently sitting there radiating light with a very specific distribution of colors that we refer to as blackbody radiation. Joining me to talk about this today is Eric Kulkers, who is part of the team in Madrid working for the European Space Agency, and he is there working on the Integral spacecraft. Hello, Eric, and thank you so much for joining us today.
Hi, Pamela.
So you work on a variety of different science topics, but one of the ones that is most relevant to what we're talking about today is neutron stars and how they actually appear to cool off and change color ever so slightly after they go through an outburst event. Can you walk us a little bit through what happens and what it is that you see?
So these neutron stars are surrounded by another star. Most of the time it's a solar-type star. This solar-type star gives matter to this neutron star, and that material goes onto the neutron star, builds up, gets hotter, and at some point it explodes. You get a thermonuclear explosion that heats up the neutron star, and that then has to cool again. And then in a matter of hours, it does the same thing.
And so this is really a case of stellar cannibalism. Each of these stars, they are binary systems. These are two stars that ended up forming probably together out of a large cloud of dust and gas that fragmented into the two separate stars. And this particular case of stellar cannibalism, when the neutron star ends up forming, it looks much smaller. It's in fact smaller in radius, but it's much more dense than its companion. And so its gravity is able to suck material off of its companion. Now, why didn't the star that became the neutron star consume its companion before it became the neutron star?
From its birth in the beginning?
Yes.
Yeah, that's a good question. Well, you cannot just if a star forms, as you say, you have a cloud of material. It starts to contract, and at some point you start to get nuclear fusion. And that's how the sun, for example, was born. A neutron star is much more denser, and that can only exist if the nuclear fusion is off, basically. Only then can you contract further and end up with a neutron star. So before the neutron star is born, before the neutron star actually is born, so to speak, nuclear fusion stops it from forming it.
So essentially you go from a case where you have two stars that are happily existing side by side. Both of them have nuclear reactions going on in their core. These nuclear reactions are producing light. And this light pressure pushes outwards on the outer parts of the star. Gravity's trying to crush inwards, but everything is balanced.
Yes.
Now, the larger of these two stars, it's going to run out of fuel first. And what happens when it runs out of fuel?
So when it runs out of fuel, it starts to, well, first you get, it burns the hydrogen. At some point there is no hydrogen anymore. Then it starts to burn the helium, and that goes faster and faster. And at some point, the whole star explodes, and material is blown out. And what you're left with is a neutron star. So things have to expand. But when the inner core of the star has to contract, and that leaves the neutron star, basically.
And I have a diagram of a rough idea of what some of these may look like. So this is a case of really, really dense. Neutron stars are actually just a few kilometers across. So you could plop a neutron star down in the center of a city and it would happily ruin the center of the city, but it would fit there quite nicely.
Yeah, definitely. It would ruin everything there, yeah.
It would, in fact, ruin the planet Earth, but it would fit in a city center. And these high-density objects, they'll actually migrate up right beside their companion, and then their gravity starts sucking this material off. Now, conservation of momentum is an evil thing, and it actually prevents the material from falling straight onto the neutron star. Now, with the neutron stars that you're talking about, is it the accretion disk that ends up exploding, or is it material that is piled up on the surface of the neutron star?
No, so yeah, so with you a little bit that image as well. So you see on the left side you saw the companion star, and the little thing, like I don't know how you call that toy. It's like
a top.
Yes. So the flat thing, that's the accretion disk, and the neutron star is, I think, on this scale is not visible, really, really tiny in the middle. And what explodes is not the accretion disk; it's really the neutron star itself. Well, the material falls on the neutron star, and that material on the surface of the neutron star, that is sort of exploding.
So essentially what's happening is this stuff is piling up and gravity is compressing it and compressing it and compressing it. And at a certain point, gravity compresses it so far that it has to explode. It's so hot, so dense that that's the only option left to it. Now, when this happens, it gives off a ton of energy. Now, when this energy is given off, what does that do to the neutron star itself?
So partly it radiates. Also, it heats the surface of itself, because there is also where the explosion takes part. That's more or less what we see, but it also heats up a little bit the inner side of the neutron star. I mean, heat goes inwards and outwards. And what you basically see when it cools, it's the heating from the inner side of the neutron star, which is slowly then again radiating out.
Now, when we look at neutron stars, it's not like we can walk up to them with a thermometer and plug in the thermometer and measure what temperature they are. So how do you figure out that this explosion heated up the neutron star?
You basically measure, in fact, the temperature. I mean, the temperature is more than a couple of million degrees. So, and that radiation peaks in the X-rays. So what you basically do is you put an X-ray thermometer there, or not of course not near the neutron star, but you put an X-ray thermometer in space, and then you measure the temperature, but then in X-rays.
Now, this process isn't like what most people are used to when you're either taking a child's temperature or measuring the temperature of the turkey you've been cooking in the oven. You don't actually have to physically connect with a neutron star to measure its temperature. What you're instead doing is you're measuring the light that it gives off in different colors. how do you get
Yes.
at the temperature by looking at it in different colors?
Well, a black body basically radiates certain temperature, but it doesn't radiate at just at one wavelength. It radiates at a range of wavelengths, and the peak radiation is at a certain wavelength, and from that you can measure basically the temperature. So you measure basically the distribution of the amount of radiation as a function of wavelength. And where it peaks, that gives you the handle on it.
So when something changes in temperature, how do you see its light change?
Well, you basically see the peak of the distribution changing. So when it heats, it goes to shorter wavelengths. Yes, to shorter wavelengths, and when it cools, the peak goes to higher wavelengths.
So with Integral and other spacecraft that are measuring the temperatures of things like neutron stars, you must be looking in different specific colors and looking for changes in where the most light is coming off of the neutron star then.
Yes, yeah, that's right.
Now, neutron stars aren't the only things that fluctuate with temperature over time, where we can take advantage of black bodies to try and understand interesting additional physics. White dwarfs are one of my favorite examples. Can you tell our audience at all about how white dwarfs cool over time?
Well, it's basically the same mechanism. They also, well, a lot of them are again in binary, also accrete matter over a certain amount of time. And again, when you have enough matter, it can build up the pressure, and then you also get some kind of nuclear explosion, and then subsequently you heat up the white dwarf and let it cool.
Now, beyond just the explosions, one of the cool things about white dwarfs is you can end up with fairly isolated white dwarfs that when they first form, they can be 10,000 degrees at their surface. But if you go back and you look at them over and over and over time, you can actually see them cool off. And how are astronomers using the fact that you can measure these things cooling off?
Yeah, that's a good question. It's basically and how they formed in the first place. If you know how they cool, you can also tell something about the interior of the white dwarf. If they cool, and for example, the amount, the cooling gives you exactly. Yeah, but it basically gives you a handle on the interior, how it's built up, how dense it is. Yes, yeah.
So for instance, when we go out and we look at white dwarf stars, and I'm going to try and pull up an image of one, we can often find them in globular clusters. And in globular clusters, one of the really neat factors is pretty much all of the stars in a globular cluster formed at the exact same time. That's just one of the neat things about them. And they all formed out of pretty much the exact same composition. So when we look at stars in globular clusters, we're essentially seeing snapshots of how an entire family where everything was born at the same time has aged over time. And the white dwarfs in these systems are such that when we look at them, we can say, okay, this one is at this temperature, this one is at this temperature, and we can actually start to make assumptions about how that entire system has probably aged. And once we understand from looking at the globular clusters where we know the ages of things, we can start to look at free roaming white dwarfs and say, this one looks like this, it has this temperature, it must be this age. So here, for instance, is a slide where I can actually hit on some of these different topics. So these things form when you go from a star with nuclear fusion in the core to the fusion shuts off and the star collapses. This, in the process, the outer layers of the star are given off. Planetary nebula when you form a white dwarf, supernova when you form a neutron star. And what you're left with is these little tiny stars. White dwarf stars are about the mass of the sun and about the size of the planet Earth, that we can then watch. And when they're isolated, once they form, the only thing they will do for the entire rest of their existence is cool off, as long as they're by themselves. So in astronomy, we deal with a lot of different black bodies. Can you explain the difference between something that's a black body and something that gives off light and is totally not a black body?
Well, basically, a neutron star and a white dwarf, they are, how do you say, clean systems with no atmosphere around. They have hard surfaces. So basically, if they are at one temperature, you just see the whole surface more or less at one temperature, and there's nothing which can interfere with it. But if you have, for example, an atmosphere, the atmosphere is not the same at every height. It has a gradient, and also, so you may see different temperatures there. The other thing is that most of the time, there you see the radiation at certain wavelength. So there is no distribution among wavelengths is not nice and smooth like in a black body, but it's just concentrated in one wavelength.
So to help people understand what we're talking about when we're talking about black bodies, this is a set of curves for objects that are a variety of different temperatures, where we perceive colors and temperatures. Scientifically, they're very much the same thing. So an object that's 3,000 degrees Kelvin will appear red to the human eye. An object that's 4,000 Kelvin will appear green, although probably not this particular shade of lime green. So as you increase the temperature of an object, it gives off more and more of its light in bluer and bluer colors. Yeah. But it's still giving off light in all the other colors as well. It's just where the peak light is coming off ends up changing as you change the object's temperature. Now, this is what you get with a black body, where the average temperature across the entire light-emitting part of the object, so the surface of a neutron star, the surface of a white dwarf, is all the same average temperature, which means you have the objects, in this case the atoms in the surface of the star, are moving with a distribution of velocities. And this distribution of velocities is what leads to the light coming out at a whole variety of different colors. Now, there are things out there that when we look at them, we don't see this continuum of radiation. What we instead see is specific emission lines. So what are some of the emission line things out there that foil us by not being black bodies?
What do you mean? What kind of systems we see which give radiation at specific?
So for instance, planetary nebula aren't black bodies.
No, that's true. Yeah. Because there you only see most of the time atomic. So an electron goes from one. How do you call that? One stable orbit around the nucleus to another one. and then in that process it emits radiation, and since it goes from since the orbits are quantized, it's always the same wavelength they are emitting.
So when we look at a star, we pretty much with our eyes perceive it as being a single color, but in reality, the star is giving off this whole variety of different wavelengths. Now, when we look at a planetary nebula, even if we look at a small area of it that seems to be one color across that entire area, what we're actually seeing is specific wavelengths of light that are being given off by the individual gases. So instead, what you get is what's called an emission line spectra. So the hydrogen are giving off light in 3 specific colors, in the blues, and then another color in the red. You end up with oxygen giving off green light, helium giving off kind of light blue light. Each of these different elements is giving off a single color of light. This is where you were talking about atmospheres earlier, because atmospheres are actually kind of evil in the sense that they absorb out specific colors and emit out specific colors. And this is one of the ways that stars, like our sun, deviate away from being perfect black bodies.
Yeah. Yeah, I mean, the sort of the behind the atmosphere, they sort of radiate in a black body. But then you have this atmosphere around it. It absorbs it, part of the spectrum, but it can also emit at certain wavelengths. That's why you end up with a horrible spectrum in that sense.
Now, one of the problems that we're dealing with nowadays is the way that we light our homes is becoming more and more energy efficient, and also more and more awful in some ways. It used to be that we had these fabulous incandescent light bulbs that heated, they did heat, but they lit our homes by heating up a filament through the center of the bulb. And when that filament heated up, it gave off a black body distribution of light. And we could buy lights that had a redder color, a more yellow color, depending on how we wanted, how hot, how cold we wanted the light in our house. And that's actually where the words come from, is the colors. Now, ironically, when we refer to a light as having a hot color, we often mean red, which is actually cooler. And when we refer to a cool light, we're often referring to a bluer light, but blue is actually temperature-wise hotter, which is just confusing, and it goes back to little kids being taught to use the blue crayon when they're drawing cold winter scenes, to use the red crayon when they're drawing hot summer scenes. But the reality is the red lights are actually cooler to the touch, and the blue lights are hotter to the touch. Now, go ahead.
Yeah, now either we have been teaching our kids the wrong thing, or astronomers are doing the wrong thing.
Well, we have the numbers on our thermometer to collaborate with us. So the numbers on the thermometer say that the red star is a lot colder than the blue star. Yeah. So I'm willing to say that we're teaching our kids wrong. And I'm not sure how to fix that.
No, we should not. Yeah.
But today, modern fluorescent lights, they're very different. Can you explain the light that's coming off of a fluorescent bulb?
Can you rephrase the question?
Can you explain the difference between the type of light coming out of a fluorescent light versus an incandescent light?
You want me to explain the physical mechanism, or
just the light difference?
Yeah, no. So again, so it's candlescent, right? Yeah, it's basically radiating. As you see, it's by heating up a spiral, and that when it's heated up, it gives off radiation at various wavelengths, and the peak is at the at the optical wavelength.
So
now the fluorescent light is more or less at one wavelength.
We were having
Or
some trouble with your audio and video. Could you say that again,
yeah,
please? Oh,
and
now.
then you heat up the spiral in the bulb. Yeah. Are we again having problems or?
Yeah, you're back now though. So go ahead and sorry, could you explain that one more time? Can you hear me okay?
Okay. So for with when we're talking about condensed light, it's the spiral. You can see it when you look into the bulb when the light is out. So you heat it up, and then basically the peak light, so to speak, the peak of the amount of light is in the optical. That's why you see it, but it radiates at various wavelengths. Now that's to give light at a certain wavelength, you have to put energy in it. You can imagine that if you have light at various wavelengths, it costs a lot of energy. Fluorescent light gives you only more or less radiation at a fixed wavelength. So in that sense, that's why you save basically energy, because you only have to put energy in one wavelength instead of a range of wavelengths.
So I have the spectrum of a standard household compact fluorescent light that I can share with everyone.
With
So
the
so if you look at this, what you can see is a normal household compact fluorescent light gives off these sections of the rainbow essentially. So there's a little bit of purple, there's a middle amount of blue, there's a peak in the green which peaks with where our sunlight peaks, and then there's a distribution of red. But this is a very different distribution of light from what we get when we look at the distribution that comes off of a normal incandescent light bulb. So with the normal incandescent light bulb, you have that entire rainbow where you can tune the peak color. Now, what a lot of people are finding is, in general, we're so used to looking at people in sunlight, we're so used to looking at people in incandescent lights, that when you look at people under fluorescent lights, they often appear to either look ill or just not look right, and the color of your wall paint may not seem the same. And it's because the light that's getting reflected off of the humans, the walls, and everything else isn't the kind of black body light that we're used to looking at. So as we change how we light our homes, we're going to have to change how we view what is a beautiful color and what isn't. So
yes.
so I've kept you here for about 30 minutes, and your internet is starting to struggle a bit. So I'm going to let you go in a second. But before I let you go, are there any parting ideas that you'd like to leave our audience with?
Are there any? Can you?
Parting ideas, any words of wisdom that you'd like to give to our audience?
That's you're surprising me with that question. Now, like I said, I mean, when we started this, the whole world is more or less built up of black body radiation, and yeah, I mean, remember that when you go out, basically.
So all of us are our own little black body radiation generators.
Exactly. Yeah.
So it's been wonderful having you on, Eric. I'm going to let you go, get back to your family, and enjoy your evening. I see that we have some questions coming in that I'll go ahead and start answering, and go over some demonstrations of how people can get hands-on in exploring black body radiation. So thank you so much, and keep doing the awesome science that you do. So I think that we've lost Eric's audio at
Okay,
this point.
thank you. It was a pleasure.
There we go. Thank you so much, Eric, and I'll see you in the future. Bye-bye. So I see that we have some questions coming in from the audience. Hal McKinney is asking, and for those of you who'd like to know how to ask questions, if you're watching this live, the YouTube video that you're watching should have a little yellow Q&A app button on it. If you click that, it will allow you to ask questions that I can see here in the Hangout, and I'll go ahead and answer those questions as I can. So Hal McKinney is asking, can you further describe what the instrument, the spectrometer, looks like when you measure black body radiation? How long an exposure does it take to get a representative bell curve sampling? Well, there are countless different ways of doing this. The most simplistic way to do it, for instance, is to take the light, spread it out using either a prism or a grism, and shine it on to a detector that's not too different from the one that is in your digital camera, either a CCD or a CMOS chip. And when you do this, you can measure the intensity of the light that is hitting each of those different pixels. And when you measure the amount of energy, the intensity, as a function of color, and you get the color information because if you spread it out using that prism or a grism, the intensity as a function of wavelength is the black body curve. Now that's the most straightforward way to do it. Now the problem is when you spread all that light out into a rainbow, you end up with not a lot of light on any one particular prism. So you need to have a really big mirror, a really big collecting surface when you want to do spectroscopy. Now another way of doing it is instead of dividing everything out into this beautiful long continuous rainbow, what you can instead do is put a filter in front of your detector and only let red light through to the detector, only let blue light through to the detector, but let through many different shades of red or many different shades of blue. Let me see if I can pull up a image of what this looks like. So when you look at the light coming through from all of these different filters, it gives you a sampling of different colors. And these samplings you can then use to say, okay, in the red I have this much light. In the blue I have this much light. And if you try and fit a black body curve to that set of filters, there's usually only one particular solution for the black body that allows you to solve for what color the object is. Sorry, this is a question I wasn't anticipating, and I'm trying to talk and pull up an image at once, and I'm not always good at that. But I found an image that I can show you. So in ground-based astronomy, the classic set of filters that we used are called UBVRI filters. U is for ultraviolet, V is for visual, R is for red. In this classic set of filters, each filter allows through a different set of wavelengths. So each of the curves in the diagram that I'm showing right now, each of these curves represents what fraction of the light from 0 to 100% the filter lets through at each different wavelength. Now, filters, glass, anything that you put light through is never going to be 100% transparent. There's always going to be a certain fraction of the light that gets reflected by the glass, that doesn't get reflected by the mirror. So every interface that your light hits is going to lose some of the light. But looking at this, you can see that the red line for the red filter gives off or allows through most of the light between about 550 nanometers and 700 nanometers. These are the red shades. Now, if I put that R filter, that red filter in front of my detector, it's only going to allow through the red colors of light. And if I measure the intensity in that particular set of colors, and then compare that to what goes through with the green filter and the blue filter, only one particular blackbody curve will fit all of those different colors. Now, trying to understand how the blackbody changes as a function of color is something that a lot of people struggle with. Now, one way that we work to try and help kids and even ourselves better understand this is through simulations. Now, in theory, you could go and you could find yourself a big old chunk of metal. You could get an infrared camera, an optical camera, a camera that can allow you to see in the ultraviolet, and you can heat that chunk of iron up and measure the colors of the light that it gives off as you heat it up as a function of wavelength, and you can measure its blackbody curve. That's hard, that's dangerous. Don't do that. Instead of actually heating up a chunk of lead, what we've instead done is gone ahead and created a simulator that you can use. Now, this is work that was led by Dr. Kevin Lee, who works up at the University of Nebraska. He's currently on loan to the National Science Foundation, and his team created the Blackbody Curve and Filters Explorer. So this is what I'm showing you currently up on the website, and we will include links to this in the show notes for this video. So with this particular simulator, what you can do is you can adjust the temperature of a theoretical star or whatever you want to pretend it is. And as you adjust it, it allows you to see how the shape of the curve changes. Now, if you want, you can highlight the area underneath the curve. You can indicate the peak wavelength. So, for instance, I can now see that at a temperature of 6,470 degrees, the most light comes off at a wavelength of 447.9 nanometers. So when you look at all of this, you can start to do experiments to, for instance, compare things at a variety of different temperatures. So I'm going to set this down here to 3,000 degrees Kelvin. So this is a temperature that it's fairly easy to come up with here on the planet Earth. This is something that we could create in labs on a regular basis. And you can see that at this temperature, the majority of the light is actually coming out at microwave wavelengths. So now I'm going to add a different curve. This different curve I'm going to do for a warmer temperature. And I can now see that things that are warmer actually end up giving off a whole lot more light. So if I take the exact same object and I just heat it to a higher temperature, that higher temperature ends up corresponding to even more light coming out. Working with this, I can do things like I can select a curve and I can say auto scale to the selected curve. So this allows me to see how things compare to that specific curve. I can say auto scale to all curves, which allows me to see both curves at once. So there's lots of different things that I can play with when I do this. Now, the Filters tab on this allows me to start to see how our standard astronomy filters, when we look at things with different colors, allow us to get completely different solutions. So I'm going to make this a little bit more visible by looking at a warmer object. So let's look at a 6,000 degree star. So now I'm looking at a 6,000 degree star. This is a star that gives off most of its wavelengths, most of its color in a wavelength that is easily visible to the eye. And you can see the purple curve is for the U filter. The darker purple, it's not actually blue, it's a darker purple curve, is for the B filter. The green is for the V filter. The orange is for the R filter. And you can see where each of these filters end up hitting within this blackbody curve. And you can see how you get different solutions for the different colors. Now, the way we refer to this in astronomy is we'll say, for instance, the blue filter minus the V filter, so B minus V color. So when I compare the intensity coming through the blue filter with the intensity coming through the visible color, the V filter, I get what's called an index of 0.45. Now, if I instead look at an object that's 7,000 degrees, sometimes it's easier to just type the numbers in. I look at 7,000 degrees, I see that my B minus V color has now changed to 0.28. So using different filters, I can get samples of the blackbody curve of an object, and I can understand what temperature it's at. So this is something that we're going to have you and your kids work on in the exercise that we've put together to accompany this particular exercise. Now I can see that I have some more questions coming in. So let me look at those questions. So Carolina Damjanska, I'm sorry if I mispronounced your name. She says, what about light from LED lamps? Can you compare this light with usual bulbs? So LED lamps are actually very frustrating when it comes to spectrums. Let me try and pull up the spectrum of a white LED. So the problem with LEDs is they are made up of a very specific set of chemicals that give off light in very specific colors. So when we light up a room, when we light up a house using LEDs, we get very weird appearances and things. So I'm downloading an image that will allow you to compare how different types of light looks. So I showed you what blackbody looks like. That's what you get from a normal incandescent light. Now, to show you what you get with other types of light, this is a graphic that comes from the magazine Popular Mechanics. So the sort of blackbody, but not quite light in the background is sunlight. Now, the reason that doesn't look like a perfect blackbody is because our own atmosphere is absorbing some colors of the light, and the outer layers of the sun are also absorbing out, but to a much lesser degree, certain colors of light. So when you combine the effects of the outer atmospheres of the sun and the much stronger effect of the outer layers of our own atmosphere, you end up with this weird lumpy plot. Now, an incandescent bulb with a normal blackbody radiation, the bulb that they're showing here has its maximum wavelength far to the red, so you're only seeing the part of the blackbody curve where it's declining down towards the blue. Now, in this particular graph, they're comparing this to an LED light that is made with a variety of different colors of light and with a compact fluorescent that, again, gives off light in a variety of different colors. And you can see each of these have a very, very different curve. Now, with LEDs, the exact curve that you're going to get varies hugely from one LED to another. So this is just the particular set of LEDs that was used when they made this one particular graph. Now I have a different one that I can show you that compares then an entirely different set of lamps. And all of this starts to hopefully help you understand why when you look at paint under the lights at the paint store, that color of paint that you're buying might look very different while you're in the store compared to once you paint it on your walls when you get home. So other types of lights that we use nowadays include things like mercury vapor lights, which pretty much only give off light at the specific wavelengths where mercury has atomic energy levels. These are the wavelengths where the electrons in the mercury are jumping up and down as they're excited by electricity. You can see again a curve for a white LED. You can see the noontime sunlight. Unfortunately, it doesn't tell us actually what that red light is through this. I'm pretty sure the red curve represents a normal incandescent bulb. And then if you're interested in the light from your red bar scanning laser that you might see at the grocery store, that again is a very specific color of light. So modern lamps, every single lamp that you use gives off a different set of colors and causes the things that you look at to look very different. So Hal has another question. He says, can you further describe, oh, no, sorry, that's the same question. Things are just showing up out of order. So sorry. I'm pausing to read questions. So Ed Thomas says, so by using the wavelengths that you talk about in Mr. McKinney's questions, these are the wavelengths with the filters that I was showing. Is this how you measure redshift? So when we look at different distant objects, or in fact even nearby stars that are moving, when we look at a star spectrum, and let me find a solar spectrum to use as an example. When we look at stars' light and we divide it out, we often see different lines in that spectrum. And the different lines correspond to different places where specific atoms have absorbed or emitted light. Where they absorb, it appears as a black line that I'll be able to show you in just a second once I get this picture. Now, knowing specifically where these different atomic lines should be based on work that we do in the lab, when we look at a star that's in motion, we don't always see the lines in the exact same place. So this is the solar spectrum. This is an actual spectrum of the sun, where you see that dark black band down in the red. That is the hydrogen alpha line. This is the line that is created when when sunlight passes through hydrogen in the outer layers of the sun, that hydrogen will absorb that sunlight and cause an electron to go from the second energy level up to the third energy level. So that's the H alpha. It's the first of the Balmer series of lines in the sun. Each of these lines is caused by a specific atom undergoing a specific transition. In the lab, we can measure exactly what wavelength this should happen. But when something's in motion, if it's moving towards us, the Doppler shift will shift each of these lines to the blue. And if something's moving away from us, it will shift all of these lines to the red. So, for instance, if the sun were suddenly to start racing towards us, this won't happen. This isn't a real thing. This is just an example. You might see that dark band that currently shows up in the blue shift more and more towards the orange, towards the yellow. And how much it's shifted depends on how fast the object is going. Now, the more interesting case that we look for is when we look at really, really distant galaxies. We look at the hydrogen Lyman lines instead. These are the transitions when electrons are going from the first energy level up to the second energy level. And the Lyman alpha line normally appears so far out in the ultraviolet that we can't see it with our eyes. We can't see it with a normal visible, sorry, my phone is ringing. We can't see it with a normal visible light telescope. But because distant galaxies are moving away from us at vast velocities, that Lyman alpha line gets shifted more and more into the red. And eventually it gets shifted so far into the red that we can see it all the way in the optical light. So when we're looking to measure redshift, we actually want to look at these specific lines that appear on top of this continuum radiation. Now, we can't always do that. So sometimes with much less accurate results, what we'll do instead is we'll say, okay, so I know what the light curve in general, what the energy distribution in general for a galaxy should look like. So we'll say, I know in general that the stars in a galaxy will produce a curve that peaks at this color, it's a little bit lower at this color. And we'll take that new curve. So it's not a black body curve, it's a different curve. And we'll look at it through different filters and using the same ideas as black body radiation. Just like we can guess at the temperature of an object and get pretty accurate using filters, we can use filters to estimate knowing what we think the light distribution from a galaxy is, we can use it to estimate the Doppler shift. That was a very long answer to your question, and I hope I hit on all of the different parts. So black bodies are one of these things where true black bodies are very rare, but they're very useful. White dwarfs are, as we hit on in the interview with Eric, one of the best black bodies that are out there. This is because white dwarf stars are extremely compact pieces of matter. The electrons are so densely packed together in a white dwarf that they essentially form a crystalline structure. And if you have a white dwarf that is made up of mostly carbon, you essentially have a diamond the size of the planet Earth. Now, with everything compacted so closely together, you have everything is at a pretty much constant temperature, and you don't have an atmosphere to create the atomic lines like I just showed you in the solar spectra. So when you look at a white dwarf, you simply get this continuum radiation that is a black body. We know that when they form at the temperature of a core of a star, so they're tens of thousands of degrees, and over time they cool off. Now, the rate at which they cool off is determined by their internal structure, so it's not straightforward calculations. People spend their entire careers trying to calculate the rates that white dwarfs cool off. But knowing that they're a black body, knowing that they're a crystalline structure, means that we can, with lots of hard work, get at this, and we can use white dwarfs to say, I know that this particular part of the universe is at least this old because the white dwarf has had time to cool off to this temperature. I know this part of the universe is at least this old because the white dwarf has had time to cool off. Now, in your classroom, you can't exactly watch a white dwarf cool. But what you can do instead is you can watch a piece of metal cool. Now, at the beginning of this lesson, I said you shouldn't go heating up giant pieces of metal and exploring the black body over all of the different temperatures. And really, you shouldn't. But what you can do is take just a regular old piece of metal, something as simple as like a classroom bell that you might use that has a wooden handle on it, something fairly small. Heat it up by putting it in boiling water. And at most of your local convenience stores, you should probably be able to get an IR thermometer nowadays. These are thermometers that allow you to figure out the temperature of your turkey without actually jabbing your turkey with a thermometer. What these IR thermometers do is they measure the temperature by looking at what colors the turkey's black body radiation peaks at. Well, you can do this with that bell that you've heated up or that other metal object that you've heated up as well. And you can watch over the course of your class as the color of the light changes. Now, another thing that you can do in reminding your kids that they are little black bodies themselves is if you have access to one, you can show your kids what they look like using an infrared camera. These cameras tend to be about $5,000. So I'm guessing most of you won't have access to them. But there's also really awesome YouTube videos out there. And I'm going to pull up an example of one of these YouTube videos that we will have linked into our lesson plan. This particular YouTube video shows you what it looks like if you look at something based on temperature using infrared radiation when you're cooking an egg. So if you could watch the universe in temperature, this is what you would see for the specific case of heating an egg. So there you can see the heated up electric coil. You can see that the pan is a little bit warmer than room temperature. You can see here the pan is heating up. It's still not as hot as what's underneath, but you can see the bottom of the pan is hotter than the sides of the pan. You can see the human glows because the human is warm. You can see that the plastic spatula doesn't glow because it's an insulator. You can see over time things continue to heat up. There's now eggs on the bottom that are heating up. And just showing kids how heat is conducted, how things glow at different peak colors depending on their temperature, can just get your kids thinking about the universe in a slightly different way. It's always nice to take all of these astronomy concepts and bring it back down to things that we deal with on a day-to-day basis. And most kids have at some point in their life seen eggs getting cooked. So this makes this just a particularly good example. Now, I will caution you, if you do have access to an infrared camera to bring into your classroom, infrared cameras can reveal different medical conditions. So be very careful when you're using the camera. For instance, if you're pregnant and you don't want anyone to know it, do not point it at your midsection, because your midsection will be a little bit warmer where that baby is working on forming. So you can also inadvertently end up revealing different circulatory disorders. So if one of your kids has diabetes, their hands might glow differently than a kid that doesn't. So in general, be very cautious about how you use the infrared camera, point generally at the faces, and if a kid's sick, don't point at them, because they will look very different if they're sick. Fevers change how you appear on infrared camera. This is one of those things that you can have fun with. You can point out different cases in movies where black bodies have come into play. So in the original series, Star Trek, which some of you and none of your kids saw live, you can go back on YouTube and you can find the old episodes where Captain Kirk is heating up a rock with his laser. So what he's doing is he's pumping energy at one specific color into the rock. The atoms in the rock are getting excited and the rock begins to glow red. You can pull up examples of night vision goggles. Night vision goggles allow you to see in the infrared in some cases. All of these different things are, again, relying on black body radiation. So this was the last Hangout of this particular school year. I think this was a kind of fun topic to end on. We were planning to end on the Big Bang, because it's always good to end with a bang. And I appreciate your patience coming back to this delayed showing that we had due to the illness that ended up getting this canceled before. We will be back in the fall, and learning doesn't stop just because it's summer. Everything that we have is online. Check out our lesson plans. Start planning out your next school year. Figure out what you want to do. All of our lesson plans are in English, and I understand many of you, that's not your native language. That's definitely not a language your kids are probably comfortable working in. If you create translations of the lesson plans we've put together, please, please, please share them back. There's probably other teachers in your nation or in other nations that speak the same language that would love to use the translations you put together. So please share those back through the Inspiring Science Education website. You can reach all of our materials by going to Open Discovery Space. Just Google it, and Inspiring Science Education is just a click away through the community portal. It's been a great year getting to work with all of you, and I hope to continue seeing you online through all of our different communities throughout the summer. So thank you, and enjoy your summer.